Hello, this is the 11th video in a series I'm doing on Fourier Series, and in this video we're going to look at the convergence of the Fourier Series based on conditions of f of x and the derivative of f of x. And what we want to show are these two results here. The first one, we're going to pick a point in the domain negative pi to pi. We're going to let this be the partial sum, and we're going to show that the partial sum converges to this relationship. So it converges to the limit from the right and the limit from the left at that point f of 0, or it's the average of those two. And that is when f of x and f prime of x are piecewise continuous and of course have period 2 pi. And so here, if the function is piecewise continuous, so there's a jump from here to here, then, and we're going to look at the Fourier series at that x, then that converges to the average of the limit from this way and the limit of this way. And if they're the same, it actually converges to f of x. Now here, we're going to let f of x be continuous, of course have period 2 pi, and the derivative of f, f prime of x be piecewise continuous. Then the Fourier series of f of x converges uniformly to f. And so this one is convergence pointwise, and this is of course uniform convergence. So let's jump right in. So by f7, which is the partial sum, we know the formula for the partial sum is this. And actually in this video, we go from minus pi to pi of this, but we're breaking that interval up from negative pi to 0 and 0 to pi. So in this video, it's actually one integral. But it's the same. We can break it up. It doesn't change it. Now in F6, which talks about is the Dirichlet kernel, we show that this integral of the Dirichlet kernel is equal to the integral from 0 to pi, and this is negative pi to 0, is also 1/2. Both of these are 1/2. As a matter of fact, when you combine this and you go from negative pi to pi of the Dirichlet kernel, it's 1. But each piece is 1/2. So then if we look at this piece here, so this is the limit from the left, this is the limit from the right. We're going to take the average of those, and we pick that because that's what this is. And so I'm using shorthand notation for these. But if you look at this, so notice this piece doesn't have anything to do with t, so it can be taken out front. And then this integral is 1/2. So you have f of x naught negative over 2, which is kind of this piece. And over here, that can be taken out and the integral is 1/2. So then you end up with f of x naught plus over 2, which is this piece. So this does equal these two integrals. And now, because the partial sum can be written like this, and this function can be written like this, we can combine this and combine this into this integral. So this is just algebra. So this can be combined with that, and you kind of see the minus there, the minus and the minus for this. Okay, so it's just algebra here. So now what we want to do is, if we let capital N go to infinity, we really hope this is 0, which means these are 0, right? This has to go to 0 and this has to go to 0. And so we're going to evaluate them one at a time. And it'd be nice that if we could just easily show that one of them's 0. And we can maybe use the Riemann Lebesgue theorem, because so if this is integrable, we multiply it times sine or cosine where this coefficient goes to infinity, and that's what we want to show, then this is 0, then it's obvious. But it's not quite straightforward that this is integrable, because remember, that we're including 0. When you plug in 0 here, it's 0, and you can't divide by 0. So we have to look at the properties of this. But if we can show this is integrable, then boom, that trivially goes to 0. And the same way here, if this is integrable, the Riemann-Lebesgue theorem says this goes to infinity. This is 0. So if this is 0, this difference in limit is 0. So then this does converge to this value, which is what we want to show. So the goal is that we need to examine this one a little bit further. So we're going to examine this one in detail, and then this one is just trivially what we did with this one. So first, we're going to look from 0 to pi. Notice we're not including 0. So f is piecewise continuous, and the sign is continuous. So clearly this ratio is piecewise continuous and integrable in this range, because at no point is this 0. So really we need to evaluate what happens at 0, the limit as it goes to 0. So let's evaluate the function here and let t go to 0. Okay, so what we do here first is we multiply it by 1. We multiply by t and divide by t. So we didn't change this. But the limit of a product is the product of the limits. So we can take this limit of this and limit of this. And this one here is the famous x over sine x as x goes to 0. So we know this one is 1. So 1 times this is whatever this is. So we got to evaluate this here. So let's just look. So in limit, this equals this, because this is 1. So now, how do we evaluate this? Well, this kind of looks like a derivative. Where f of 0, x0, plus, it's whatever the limit is, and then we're letting t go to 0 to this value and dividing by t. So this is like a limit, but one of the conditions was that the derivative is piecewise continuous. So this exists because the derivative is piecewise continuous. So this limit exists because one of the conditions is that the derivative is piecewise continuous, and this is the derivative. So it's piecewise continuous. Thus, this ratio, is piecewise continuous on this range. The limit exists as it goes to 0, and of course on the rest of the range it's piecewise continuous. So the whole thing is piecewise continuous, which means it's integrable on 0 to pi. Now similarly, we can do it for the other function and show that this is integrable on negative pi to 0. Now what that means is when we look at the limit as n goes to infinity of this difference, which is this difference, we can employ the Riemann-Lebesgue theorem, F1, right? So this is integrable, and that's sine, that goes to infinity, that's 0. Same way this is 0. So we have 0 plus 0, which is 0, which says this limit is 0. And since this doesn't have anything to do with n, it can be taken to the other side. And it says that the Fourier series does converge to this. And if the f is continuous, of course, then this drops out and just becomes f of x. And that's what we wanted to show. Now part B, we want to show that it's uniformly convergent. That if f is continuous and the first derivative is piecewise continuous, then it converges uniformly. So here we're going to let this series be the Fourier series for f. And then this is piecewise continuous, so we're going to let this be the Fourier series for the derivative of f. Now Bessel's inequality, which is video F10, we show that these are finite. It's an inequality, and this is the lower bound of the inequality. So these are all finite. Now what I want to do is I want to look at these coefficients Cn, and I want want to show that there's a relationship between these two coefficients, dn and cn, but we'll look at cn and dn separately. So here are the coefficients. Now it's video F4 where we discuss orthogonality and the orthogonal basis functions that helped us drive these Fourier coefficients. And we showed that this is what it really is equal to. So Cn is this integral, and this is f prime. So this is, remember, these are Fourier coefficients with respect to f prime of x, and then we derived them there. Now let's look at this one here, and let's integrate it by parts. And if you've made it this far, I'm not going to go into much detail on integration by parts because you probably know it at this point. So this is equal to this when you integrate it by parts. Now this, the 1 over prime is times this and times that. So if we multiply the pi in here, this is this. Okay, so how is this 0? Well, here's it. So when you plug in pi and negative pi, you get the same thing because cosine's an even function. And f is periodic with 2 pi. So f prime, f of pi and f of negative pi are actually the same thing because they're periodic. So you're plugging this value in and then subtracting it, plugging this value in, but it ends up being the same. So you're taking that function and subtracting the same thing, so it's 0. So we do just get this piece. But this function with the pi included, that's how we define the Fourier coefficients an. So it's the Fourier coefficients for f of x. So Cn is actually just n times a. And now we can integrate this by parts and show similarly that dn is actually n times bn. Okay, so how's that help us? Well, we know by Bessel's inequality that this sum of Cn squared is finite, the sum of dn squared is finite, but if Cn is an squared of an, we know it's finite. And then if dn is finite, then we know that n squared bn squared is finite. Now by the Schwarz inequality, which is this piece, we know that the sum of the absolute value of an, which if we multiply this times 1, times n divided by n, we get this. So this piece, so this is the Schwarz inequality, which we're not going to prove, you can look it up, that this sum is less than if you take each of these by themselves, square them, and then take the square root of that whole sum. This is true. Well, this here, 1 over n squared, this sum is the Basel problem, and we know that's finite. And we take a finite number and take the square root of it, that's finite. And we just showed that this is finite, so this is finite. So we have 2 finite sequences multiplied together, so it's finite, so it's finite. So an is absolutely convergent. So thus this is finite. Now notice if we were to multiply an times something less than 1, it gets smaller. And so we're going to multiply an times this cosine of nx. So this goes between, 1 and minus 1. So if we multiply this, it's actually less than an. Okay? So now another theorem, and of course whenever you prove something, how far do you go back? We're going to make another assumption here about the Weierstrass M test. So it says that if we have a sequence, or a function that's less than or equal to a positive constants that their sum is finite, it says that this sequence converges uniformly. That's what this M test says. And so since these are positive constants and the sum is finite, then this sum converges uniformly. Okay, and so we can go through this rigmarole again, and we can show that this sum also converges uniformly. So therefore, this sequence converges absolutely and uniformly. So here, so if we put absolute values around this, then it's less than or equal to, you know, the individual sum of this plus the sum of this with absolute value, which is this, which is it's absolutely convergent, and this one's absolutely convergent. So this is absolutely convergent. And it's also uniformly convergent. You know, if we note that the uniform limit of a series of continuous functions is continuous. Thus, the Fourier series converges uniformly to F, and that's what we wanted to show. Well, that's all I have for today. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.